So let's hear your plan for this semester, Bill.
Um, my plan is to study real analysis, study algebra, and study either DG or GR, which are the same thing.
Yeah.
But I just don't know which language, math or physics.
Yeah, they're the same language. It's just they're two different perspectives that are useful. But two like mathematical perspective is ultimately more powerful.
Yeah.
And more general. But like reading the book by Sean Carroll on gravity is helpful. Like it's an excellent book, but you need both. You need the mathematical formalism of a book on Riemannian geometry.
Two. It's book.
I mean, I recommend two. You can find what works best for you.
Yeah.
I mean, if you want to do a reading with me, you can catch up to me. Because I'm in two. I think I'm in chapter 9 or I'm on chapter like 10 or 11. But
That's pretty fun.
yeah. You'd have to read a lot.
Yeah.
But the chapters are pretty short. They're not like it's like 100 pages. I'm like page 100 out of 300.
A successor to the Manifolds book,
Yeah.
so it builds off of it, or is it kind of its own deal?
No, it builds off of it. The Two's Manifolds book is a prerequisite.
Okay.
It builds directly off of it. What book are you gonna use for real? What are you gonna do for real analysis?
I'm not sure. I was thinking of just going through the MIT OpenCourseWare. Or actually, I was thinking, Justin gave me all of his analysis notes and exercises from Chaika's class that he taught last spring. I was thinking of going through that and then supplementing it with a textbook that you recommended.
Yeah, I think that's a pretty good idea. So you have all the stuff from Chaika's real analysis?
Yeah, all of his notes and all of his exercises.
And then, yeah, I don't know. MIT OCR, I'm not familiar, or OCW, I'm not familiar with how good that is for upper level classes. I've only used it for
Like calculus and stuff.
earlier level classes. Excellent for earlier level classes like calculus, linear algebra.
Yeah.
It's excellent for those earlier level classes, but for a grad real analysis, I just don't know. I'm not sure.
Yeah.
But you can certainly find some lectures online.
Well, I saw the algebra version was taught by Aaron. I don't know if they have supplementary lectures, but they do have syllabus for the course and everything.
Well, there's a good course from Harvard. Is that by Arden? No.
Well, I think the one I've seen that one though, and it follows Arden's book.
Yeah.
Yeah, that one is really good. That guy's lectures are really good.
Yeah, I mean, I don't know. I feel like algebra is something that I need to work on.
Yeah.
Because I could have read all of Arden. I only read chapter 2 of Arden. I could have read more of Arden.
Yeah.
It's kind of my weaker. I kind of took the structure of a class for algebra. Some of these things, like for me, algebra is not my immediate interest, or like it's not what I feel like I need to learn the most right now. Maybe like Lie algebras and Lie groups. But algebra, I feel like I kind of put off, and so I have to force myself to learn it by basically taking a class. Like I'm going to force myself to take the grad algebra class just so I have to learn it, because otherwise I just have other priorities in my study. I'm never going to learn it. There's so many things to learn, dude. Ergodic theory, thermodynamics, statistical mechanics.
Yeah.
I'm doing a reading course in functional analysis, a reading course in ergodic theory.
Is that also with Chaika?
The reading course in functional analysis is the Chaika.
Who's doing ergodic theory?
Kurt Vintage.
It's crazy.
It's kind of hard. It's like kind of annoying. But then I'm teaching myself differential geometry. That's the thing. For my research, I need to learn differential geometry so that I can now move to doing optimal transport on manifolds, right? Like I understand the basics of the theory of optimal transport on Euclidean space. Obviously, I need to learn way more about that because I don't fully understand yet the geometric intuition behind the Kantorovich potentials. I think that there's a wealth of intuition there that I'm lacking, right? Like I've read the books several times. I've read several different books on the topic over and over again, but there's still some geometric insights. Like I know a lot of the theorems and I know how to prove a lot of the key duality theorems, like step by step, and I understand some of their motivation, but I think the geometric intuition for me is not quite there. The geometric intuition is just not as much as it could be. Now, for example, when I'm studying differential geometry, there's a ton of geometric intuition, basically dealing with normal vector fields and Gaussian curvature, right? These normal sections of, maybe a submanifold of R3, or like, a regular submanifold of R3, a regular embedded submanifold of R3, right? You look at its normal vector field, and you can find a normal vector field locally, a smooth normal vector field, you can find that locally just by the fact that it's a regular submanifold, right? Mm-hmm. And then you basically look at how that normal vector field changes along different directions. You've seen this before, right?
Yeah.
And you look at that, you get the shape operator. Have you learned about the shape operator? It's just it inputs a vector and outputs the directional derivative of the normal vector field in that direction of the vector that you input, and then essentially that is defined to be the negative of the shape operator. So the shape operator somehow encodes the directional derivative of the normal vector field up to a minus sign in a certain direction. Okay, and from the shape operator you can build you look at the Riemann curvature tensor, which is a measurement of how much the connection your Riemannian connection deviates from being a Lie algebra homomorphism. Okay, so there's a lot that goes into that. Basically, let me just say, okay, so that's how you define the Riemann tensor. It's that measurement of how the map from vector fields to the affine connection deviates from being a Lie algebra homomorphism, and there's a unique Riemannian Riemannian connection which is compatible with the metric, and what's the second property it satisfies? Torsion free, right? And then essentially you use that Riemannian connection. You look at the Riemann curvature tensor with respect to that Riemannian connection. You look at the Riemann curvature tensor there, and it's essentially you can figure out what the Riemann curvature tensor is based on the shape operator. Essentially, you can get an equation for the Riemann tensor in terms of using the shape operator. In particular, the shape, you can get an expression for like also the Ricci curvature tensor using the Riemann. Obviously, you can track the Riemann tensor, but these are just the concepts that I'm covering right now in differential geometry. The point is that ultimately I want to apply this theory to optimal transport, because if you understand like the framework of differential geometry, you basically understand the structure that underlies your space. So it's like you understand the canvas that you want to paint a picture on.
Yeah.
Right? The canvas could be like space-time, for example, right? And at the end of the day, you have all these things occurring in the background of space-time. Our entire lives occur in the background of space-time, right? So what you're studying is basically the canvas on which one should paint.
Yeah.
But I think optimal transport on a Riemannian manifold, once you understand the canvas, optimal transport allows you to paint, literally, on the Riemannian manifold. Just basically by understanding, you can do the full Lagrangian and Hamiltonian mechanics in infinite dimensions. Like,
that's insane.
Instead of modeling this phone as a point particle in R3, right? I could model this as an exact mass distribution in space-time that's evolving every point of this I can keep track of to an arbitrary degree of accuracy. Obviously, this is just the mathematical utopia, right? When it comes down to the physics of the real world, there are always measurement errors, etc. But like in the mathematical utopia, you'd have a perfect description of an object, and it's not just a point particle. In fact, it's basically a collection of an infinite amount of point particles. You can view it. You can approximate every measure. Okay. So if you take a measure, take for example a probability distribution. Okay. Are you familiar with probability distributions? They're like a measure with total mass 1. They're a positive measure with total mass 1. I guess, yeah, you need to learn measure theory. So it's not too hard to understand what a probability measure is. A probability measure just looks at every point on the space, and assigns it a certain mass. So a probability measure can be thought of as a mass distribution throughout space. Okay? So think about it as a mass distribution that integrates to 1. And if you integrate any certain region, you are understanding the mass of that region. Mm-hmm. Okay? So a probability measure is basically a mass distribution. Now you can have a delta mass at a point, right? And that's just saying all the mass is concentrated at a single point. That's just a point mass that you deal with in classical mechanics. Yeah. So really classical mechanics in finite dimensions, you're just looking at delta Dirac masses. You're looking at mass distributions which are centralized at a single point. So you're doing all the math with delta masses, which are a type of measure in a larger measure space of all possible mass distributions. Okay? Now this larger measure space, okay, you can embed larger measure space, you can put a metric on it through the optimal transport. You can put a metric on the space of measures and understand the distance between two mass distributions. You can understand that distance basically by the cost of transporting one mass distribution onto the other. Okay? Yeah. According to, and if you choose the quadratic cost, so if you choose the cost that's a quadratic distance, so the cost of transporting a point x to a point y is x minus y squared in absolute value. Okay? That right there gives you a very, very special property that if you have any two mass distributions, okay, mm-hmm. and I believe one of them has to be absolutely continuous with respect to the Lebesgue measure. So that just means it doesn't actually concentrate mass at a single point. It's like a smooth mass distribution. There's no infinite mass at any point, basically. Or there's no infinite mass assigned to any surface or set of dimension which is less than the dimension of the space. Does that make sense?
Yeah. And so optimal transfer is an analogous metric to other things too?
Yeah, no, well, I guess what I was saying is that, what I was going to quickly say is that if you have those two measures, one of them is absolutely continuous with respect to the Lebesgue measure, in the case of the quadratic cost, you are guaranteed not only an optimal transport plan to move one mass onto the other, but in fact, you are guaranteed that optimal transport plan is deterministic, so it preserves mass, okay? Preserves mass locally. Mm-hmm. Locally does not split mass, and it is the gradient of the convex function. Okay? It literally has a super specialized property.
Yeah.
And then you basically, Benema and Brenier, this is where the physics comes in. Benema and Brenier basically they came up with a fluid dynamical reformulation of the optimal transport. So essentially, picture two mass distributions, okay? Maybe two Gaussians in space. Just picture two Gaussians in space, right? And the idea is that the path which transports a continuous path in the probability measure space, which optimally transports one Gaussian distribution onto the other, or one mass distribution onto the other, okay? That continuous path can be characterized as a minimizer of a certain functional. What is that functional? The integral of the velocity field squared against the mass distribution, where the velocity field is among the velocity fields which solve the continuity equation with the mass distribution. So essentially the velocity field solving the continuity equation with the mass distribution is telling you that the velocity field is actually pushing forward the mass along that curve. So basically it's like the tangent vector. It's like the tangent vector to the entire distribution. It's really a tangent vector field, right? That basically is tangent to this curve of mass being continuously moving through space. And instead of having a tangent vector that's a single vector on a single curve, you have an entire curve which is a curve of mass distributions. And the tangent vector to that curve is an entire vector field in space that pushes forward the mass along its flow lines. Every vector field in space is going to be locally integrable. Okay, that's a theorem that you learn in differential equations. If the vector field is smooth enough, right? If it's like a sufficient regularity vector field, it will locally induce a flow, which is a set of differential equations that basically produce curves that are tangent to that vector field, right? And so every vector field has a local flow. You covered that in manifolds, right?
Yeah.
Okay, so then the idea is, this vector field, which basically that flow, you push forward the mass along that flow, and that's the definition of like that's what it means to solve the continuity equation, is the mass distribution is being pushed forward along the flow of the vector field, okay? Now, among all those possible vector fields, right, the transport cost, okay, or the optimal transport curve, literally a continuous curve which optimally transports one mass distribution onto the other, is the curve which minimizes the kinetic energy, basically.
Mm-hmm.
It's literally an infinite dimensional version of a free particle. It's a free mass distribution. It's minimizing a kinetic energy functional with no potential energy. And those are the geodesics in the measure space. So it's literally an infinite dimensional version of classical mechanics. You have the framework to do classical mechanics in infinite dimensions.
And that's insane. It's kind of messed.
And not only that, but you can do it on Riemannian manifolds, which means you can do general relativity. And you can do general relativity in infinite dimensions. And this is getting used for general relativity. But it's just now being born. Like, it's a very new field. This is like a big deal, bro, for the future of physics.
Yeah, that's correct.
I don't think people realize like how big of a deal optimal transport really is. They kind of hear the name and they're like, oh, this is just some finance, or you're just like optimizing traffic patterns, or like, no, you're literally putting a metric on the space of probability measures. Like, you're turning the space of probability measures into something kind of like a Riemannian manifold, literally. An infinite dimensional.
Yeah. It's insane machinery.
Yeah.
I'll have to get into some OT.
So tell me, before you get into OT, you're going to have to get into some real analysis. You need real analysis. That's the biggest prerequisite.
Yeah.
So what are your plans for learning real?
Yeah, I need to come up with a study schedule, how to split up my time with these 3 classes, but I want to just go over those entire notes and do every single exercise.
Okay, Chaika's notes? That's smart. Yeah, that's smart.
Well, reading a textbook.
Can I grade your exercises?
Yeah, I would be actually happy to.
I would be happy to grade them. I feel like I would learn.
Yeah.
It'd be interesting to grade.
Yeah.
Chaika's homeworks are pretty hard. I had them for grad real for a little bit. Yeah, I withdrew that semester because I was like not wanting to do classes. Like, I was taking way too many classes.
Yeah.
Got sick of it.
Yeah.
So.
And you felt like you were learning it all yourself, right?
Well, yeah, I felt like I wanted to learn everything by myself. I felt like I was more efficient. I was spread too thin. That's the problem, is that I was trying to learn all these different subjects, and so I felt like I wasn't learning any of them, right? I felt like I wasn't learning anything. That's why I withdrew. I didn't withdraw because of grades. I had straight A's when I withdrew.
Yeah.
I withdrew because I felt like I wasn't learning anything at all, because I was so spread thin. The only class that I stayed in was classical mechanics. I stayed in classical, but I withdrew from everything else because I was like, I'm just so tired of not learning anything, because I felt like, I just felt, and that I feel like is a problem that I still struggle with, is overburdening myself with too many topics. I think that, ultimately consistency matters in math, and time matters. You have to focus in on a couple subjects.
Yeah, we talked about things before, and I think there's kind of a problem with education. We just take a class, move on to the next one. Take a class, move on to the next one. And I look back, I'm like, damn, do I even freaking know the stuff that I took a class and got an A in?
Well, I think that this underlies an even deeper, I agree that that's a huge problem. I think that there's an even deeper problem right now in mathematical education, which is that it's the tendency of theorems to be taught without true motivation, without true intuition of what they actually mean, right? Like, for example, this proof on the change of variables theorem from calculus. I've done the change of variables many times throughout the course of my undergraduate education, but never did I understand it geometrically at the level that I currently do, because I decided to make a YouTube video on it and thought about it nonstop for like 3 or 4 days and tried to prove the theorem myself and read the proof in Folland, was not satisfied with Folland's proof. Or at least I was satisfied. Folland's proof is excellent. Folland's proof is very excellent, but I read through that proof and tried to think about what was happening geometrically. Because it's a very geometric theorem. I mean, it's you can visualize the theorem, right? You can visualize how the theorem works. You can see this change of variables, this diffeomorphism on your space. You can picture a plane, a rectangle, and wrapping it around to create the circle for polar coordinates. That's a diffeomorphism. Taking the plane where the angle goes from 0 to 2 pi, the radius goes from 0 to your radius. Take that little rectangle and bend it into a circle. That's the diffeomorphism that is behind polar coordinates. And it's locally morphing the area, and the area is locally getting morphed by a factor of r, right? That's why we have an r dr d theta, right? But nobody teaches this. I didn't learn this for years, and I feel like this is the main problem with our education system today, is that we are basically taught these theorems and these ways of doing math and solving problems that we don't fully understand. And we move on and use the formula, get the answer, and even at a high level, we know how to like build a proof. We know how to like follow the algorithm to write a proof. There's this algorithm, let epsilon be greater than 0, blah, 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 blah. Then you start your proof, and you develop over the years, you develop an algorithm for writing proofs, and it's easy to get lost in that algorithm. It's easy to just become too comfortable and not understand what you're actually proving.
Yeah, like you said, you're just going through an algorithm rather than like thinking about the problem itself. Just, I don't know, maybe thinking more about the solution than the problem itself.
Yeah, and I mean, this also happens when you read textbooks. Like, we just read a textbook, we follow how the author proves the theorem, and then just move on. We kind of just take the author's perspective as the end-all, be-all perspective, rather than taking time to meditate on everything that we learn from our own perspective, formulating these ideas in our own minds, right? Yeah. We also just depend on chalkboards, we depend on paper, we want to write everything down in notes. Write everything down, make sure you take all these notes, but we're taking notes of things we don't understand. And we're just memorizing like a lot of material, a lot of definitions, a lot of constructions. Maybe we have some intuition behind a lot of them, but some of these theorems we lack intuition for. The reality is,
Yeah.
And there's different types of intuition. There's geometric intuition, there's algebraic intuition. I feel like we're really taught to just develop our algebraic intuition above our geometric intuition. I feel like our algebraic intuition is just way higher. The difference between like writing with my right hand and my left hand.
Yeah, I agree. I literally did that today while doing foundations tutoring for just like proving the norms. I didn't think about that geometrically for a second, just all algebraically. Yeah.
But I think that, geometric intuition is more difficult.
Yeah.
And also sometimes can be limiting.
Yeah.
Because some things are just too complicated for us to even fully visualize.
Draw a picture on the chalkboard to get a picture of what's going on. Yeah.
I mean, I think a great example for that is the quaternions. Like, trying to visualize the quaternions is pretty hard. There are ways to do it. There's some great 3 blue 1 brown videos on the quaternions, by the way. There are ways to do it, but like, they're really hard to wrap your head around.
Yeah.
What do you think of the quaternions?
I don't know much about them. But
yeah, I mean, you can think of them as, well, the way that the most beautiful part about the quaternions for me is the way that they encode 3-dimensional rotation. They're also like, basically, you learn the Pauli spin matrices, quantum mechanics?
Yeah.
The Pauli spin matrices,
Yeah.
are like in the way the algebra that they form is in bijection with the quaternionic algebra. They're basically the quaternions. Physicists do math with the quaternions all the time, and half of them don't, maybe less than half, but many of them don't actually know they're dealing with quaternions. I've seen that several times. I mean, but like quantum physics really is a quaternionic theory at its heart. Think about it. It's the heart of quantum physics is anti-commutativity. The quaternions are the number system, the first number system where we lose the commutativity. I saw.
That's interesting.
Yeah. So, I mean, there's quaternionic quantum field theory. One of the founders of quantum field theory wrote a book called Quaternionic Quantum Field Theory, which, I feel like quantum mechanics should be done in the quaternions. It doesn't make sense for it not to be done in the quaternions. It's literally a quaternionic theory. The interesting thing is, what about the octonions? What if we made a physical theory with the octonions? What would the lack of associativity be able to capture in the physical world?
I don't know. That's crazy to think. Maybe there's some advanced theory that's the next step.
Yeah, I mean, I think what I was describing with optimal transport is probably the right way forward for physics. Like, I really believe that. I firmly believe that. That's a huge statement. Obviously, there are many paths forward, but I think that the biggest problem right now for quantum field theory is the lack of mathematical rigor, and in particular, the path integral. The path integral is not mathematically well defined.
Yeah.
I believe that the path integral needs an infinite dimensional space and the infinite dimensional calculus, which is offered by optimal transport theory. Because optimal transport theory, I believe, can correctly formalize the Feynman path integral. I do believe that's a path forward. And we've shown that there are these things called the Madelung fluid equations. The Madelung fluid equations are equivalent to the Schrodinger equations, okay? So going back to quantum mechanics, the Madelung fluid equations are equivalent to the Schrodinger equations. When you view the wave function, you basically split the wave function to its radial component and its angular component. The radial and angular components of the wave function satisfy a system of fluid equations in real numbers. It's no longer a complex equation, right? The Schrodinger equation is a complex valued equation, right? But if you separate based on the radius and the angular part, you get a system of real PDE, which are a fluid dynamical system called the Madelung fluid equations, okay? Turns out that the Madelung fluid equations can be shown to be the gradient flow of the entropy functional in a stochastic generalization of optimal transport theory. Optimal transport theory has stochastic generalizations. Those stochastic generalizations can provide variational principles behind the Schrodinger equation. What is the path integral? Essentially, the path integral provides quantum mechanics with its variational structure. That's what the path integral does, right? Mm-hmm. Because, quantum mechanics is normally done in the Hamiltonian formalism, right? The Hamiltonian formalism doesn't have the same variational structure as the Lagrangian formalism does. But the Lagrangian formalism is, a kingdom which contains general relativity. The Lagrangian formalism is is very compatible with general relativity, not as compatible with quantum mechanics, quantum field theory. The Feynman path integral tries to bridge that gap and essentially provide a variational principle for the quantum mechanics theory. But the path integral lacks the infinite dimensional structure needed to accurately create a variational principle for quantum mechanics. Optimal transport gives it that structure. And it's been shown. It's literally, I have a paper written by a physicist basically deriving the Schrodinger equation, the Madelung fluid equations, as the gradient flow of an entropy functional, think about that, an entropy functional in a stochastic generalization of optimal transport.
That's what?
Yeah, that's a big deal. That's a huge deal. That's a really big deal. And think about this. Optimal transport has deep connections to entropy, okay? Entropy is very critical to statistical mechanics.
Yeah.
And the idea is that previously do you know the heat equation? You took PDE, right? The heat equation, is the gradient flow. If you look at, it's the gradient flow of the Dirichlet energy, okay, with respect to the L2 metric, I believe. Yeah, the L2 norm. I'm pretty sure it's either L2 or L1. I'm almost positive it's L2. Hey, we can look it up. Yes, dude, these slides are fire. I just found some good slides. Whoa. Dude, I just found really good slides. Yo, Gradient Flow by Chang Liu. Yo, y'all have to check out these. Just wonder if they can see that. These are crazy good slides. Anyways, I'll just wrap it up, but I was just going to say the heat equation is the gradient flow of the Dirichlet energy with respect to the L2 metric, okay? However, the Dirichlet energy, it's not obvious. There's no obvious physical kind of variational principle. There is kind of a variational principle. If you think about the Dirichlet energy, it's the integral of the gradient of the function squared, okay? So that means if that integral is really large, then you're going to have heat, which is kind of vertically, locally, you're going to have a large heat gradient. And so that's going to cause, that's not a very stable state in terms of the heat equation, in terms of heat distribution, right? Heat distributes evenly throughout. So if you have this local vertical separation, which is encoded by a high value of the Dirichlet energy, then of course, the system is not close to equilibrium with respect to heat flow. And so, in fact, if you do a path that minimizes a path in L2, okay? Path in L2, which minimizes the Dirichlet energy, it's equivalent to the heat equation, okay? So there are physical interpretations behind that. However, get this. So that's with the L2 metric. The L2 metric is a vertical measure of distance between mass distributions, right? It's a vertical measure of distance between two mass distributions because you integrate their difference pointwise squared, and that's a vertical distance. The Wasserstein distance is a horizontal distance, okay? It's a horizontal notion of distance which captures our correct intuition about distance of mass distributions in the real world. It's horizontal distance, okay? Now, well, of course, obviously, it might be useful to think about vertical distance in some cases as well, right? It's always important to think about both possibilities. But with this horizontal notion of distance given by the Wasserstein metric, which is optimal transport, okay, you can show that, in fact, the curve which minimizes the entropy functional is the heat equation. The gradient flow of the entropy is the heat equation. That is profound. Because, think about it, there's a deep physical reason why the heat equation represents diffusion. Applying the heat equation is the way to maximize entropy of a system. And that's the law of thermodynamics. For a fixed energy, you have entropy always increases. Now, if the energy is not fixed in your system, then you have that the free energy is increasing. So actually, the gradient flow of the free energy functional, if you take the gradient flow of the free energy functional with respect to the Wasserstein metric, okay, what you get is essentially a transport diffusion equation called the Fokker-Planck equation. And these equations are fundamental in physics. So, the heat equation is just the Fokker-Planck equation with no drift, right? And it represents just Brownian motion, right? It represents essentially the probability distribution function of Brownian motion. So where is Brownian motion? If I start a Brownian motion particle, what's the probability that it ends up in this certain region? That probability distribution satisfies the heat equation. If you take a Brownian motion with drift, then the probability distribution function, which kind of encodes the likelihood of finding the particle at a certain point, right?
Mm-hmm.
That probability distribution doesn't evolve according to the heat equation, it evolves according to the Fokker-Planck equation, which is the gradient flow of the free energy functional with respect to the Wasserstein metric. Now that's a deep physical intuition. That's deeply tied and agrees with our thermodynamic principles and the fundamental thermodynamic laws that govern statistical mechanics. But it has only been shown that the free energy functional, the gradient flow of the free energy functional is the Fokker-Planck equation. That has only been shown through the Wasserstein metric, the W2 metric, that I was talking about, which is the optimal transport metric where you use quadratic cost. The quadratic cost is very special. It has very special geometric properties. And so yeah, this is opening the door to like huge advancements in thermodynamics, huge advancements in physics.
Yeah. It's crazy.
Yeah.
I don't know like much of what you said in the last few minutes, but that's crazy.
Yeah.
Brownian motion and all that stuff, but it's crazy the potential that it has just to explain physics itself.
Yeah.
In a like much bigger capacity.
Yeah. And you'll get there, bro. Real analysis first, one thing at a time.
Yeah.
I really think that, what do you know about real analysis currently?
No, not much. I mean, other than just to explain the basics of calculus. But once we get into measuring and stuff, nothing yet.
What's the measure of an interval?
The length of the interval. I know that.
What does it mean to measure a set? What geometric property are you trying to capture when you measure a set?
I don't know, like I guess just with real numbers and stuff, just length and volumes and stuff like that, but for an arbitrary set, I'm not sure.
It is volume though. It's just the volume of that set. It's trying to basically measure the volume of the set. And if you were given a weird set, say I took a sphere and I kind of just applied some diffeomorphism to it and made it kind of strange looking,
Mm-hmm.
how would you find its volume?
I don't know if you'd separate it all out into individual things or like just take an integral of it somehow.
Yeah, use the intuition behind the Riemann integral. The intuition behind the Riemann integral is key to learning all of measure theory, right? The Riemann integral is probably the greatest technological tool I've ever seen, or one of them. It's an insane technology. Just on a tangent, like people just memorize how to do integrals, like integral of x squared is x cubed over 3. And they kind of lose the significance of the integral. If you think about why do we care about the integral? Well, why do we care about 2 plus 2? Do you want to know that 2 plus 2 is equal to 4? Like, do you think that that's useful information to know?
Sure, I don't know. It's not
Definitely. If you were the only person in the world that knew how to add, nobody else knew that would be insanely powerful. That's a powerful tool. That's a powerful tool.
Sure.
The integral is a basically superpowered form of addition. The ability to add together a bunch of small pieces, an infinite amount of pieces. That is an extremely powerful tool. And the Riemann integral itself is the most geometrically intuitive, which makes it, honestly, the most powerful in my opinion. I mean, I think the Lebesgue integral is obviously more powerful in a mathematical sense. But, and I think that the key intuition, the difference between the Lebesgue integral and the Riemann integral, okay, the only difference in intuition is the Riemann integral partitions the domain into cubes, basically. And that's how you would try to measure this weird oval that I was talking about earlier. You'd try to break it up into cubes. Break it up into small cubes as best you can, and then add the volumes of all those small cubes.
Yeah.
Right? So that's the Riemann integral intuition, and that's a critical intuition to have. Well, actually, no, that's the intuition that goes behind the Lebesgue integral too. Okay? The only difference is when you're integrating a function, with the Riemann integral, you partition the domain of the function, right? So you partition the domain into some intervals, and then you calculate the area of those boxes underneath the graph of the function, right? With the Lebesgue integral, you partition the range. So you look at you basically partition the real line, if the range of the function is the real numbers. It doesn't have to be, but if the function is mapping into the real numbers, then you partition the real line, and then you ask what's the inverse image of each of these subintervals under the function f, right? The inverse image might be some weird set if the function's weird. But that weird set, you know how to measure its volume via measure theory. So you can partition the range of the function. Look at each of the intervals of my partition of my range. Look at the inverse image of those intervals under the function.
Mm-hmm.
They might be some weird set.
Yeah.
But you can measure that set using measure theory and then perform the same process of approximating f on this small interval, approximated as a constant value. And so you can approximate f essentially by these kind of indicator functions of sets, right? Take a set and you have its indicator function, that's just 1 on the set, 0 outside, right?
Yeah.
And you can scale by those indicator functions.
Uh-huh.
And so you're basically approximating a function as a sum of these indicator functions, which a linear combination of these indicator functions. But the thing is, the indicator functions can be over crazy sets. They don't have to be over intervals like the Riemann integral. The Riemann integral basically is equivalent to representing the function as a sum of indicator functions over cubes, right? The Riemann integral approximates a function. To do the integral, you approximate a function by a linear combination of indicator functions over cubes. Does that make sense?
Yeah.
Now, in the Lebesgue theory, you represent a function as the linear combination of indicator functions over sets, which are measurable. Measurable sets are a much broader class of sets than just cubes, but it turns out that for a measurable set, you're going to be able to approximate it by an infinite number of cubes in the Lebesgue measure theory. So it's essentially, you're focusing on the sets themselves, finding the volume of those sets before you try to do the integral. Yeah, and then I guess the last thing I should say is that the way you measure a set, if you want to measure the volume of a set, how do you do it, right? What's the construction? Well, you have sets that you know how to measure, namely you have cubes. You know how to measure the volume of a cube, okay? Then you essentially look at the covering of this set by cubes. And you ask, what's the infimum over all possible coverings of cubes? If I cover this set in I could cover this set in an infinite number of ways with cubes, right? What's the best covering? Or not just the best covering, it doesn't have to be achieved. It doesn't actually have to be achieved by any fixed configuration of finite cubes. But the question is, what's the infimum? What is the infimum over all possible cube coverings of my set? The infimum volume. That's the measure of the set. Okay? So what's the measure of the rational numbers? Okay? Well, the rational numbers are 0. Now let me tell you why. The measure of the rational numbers is 0. Let me tell you why. Fix a point. You can enumerate the rationals that are countable. I'm going to cover the rationals now by cubes, which in this case is intervals because we're in one dimension. I'm going to cover the rationals by cubes. How do I do this? I want basically enumerate the rationals because they're countable. So put them into a sequence. And then at each point in that sequence, I want to attach a cube around it of radius epsilon times 2 to the minus n, where n is the index of the rational number in that sequence. Okay? Then if I add up the volume of all those cubes, I'm adding up epsilon to the 2 to the minus n. That's a geometric sum that converges to epsilon. Therefore, for any epsilon, I can cover the rationals with a covering of cubes whose volume is epsilon.
Yeah.
But epsilon is arbitrary, therefore the measure of the rationals is 0. And so now, how do I integrate a function using the Lebesgue integral? How do I integrate a function which is 1 on the rationals and 0 on the irrationals? I just look at the inverse image of 1.
Yeah.
What is its measure? 0.
Yeah.
Therefore the integral is 0.
Yeah.
So you can deal with more complicated sets
nice
in the domain.
Yeah.
Yeah, so that's basically the Lebesgue integral.
That's cool.
And then you're going to satisfy, there's 3 theorems that you need to know. There's something called the monotone convergence theorem, the Lebesgue-dominated convergence theorem, and the Fatou's lemma, basically. So first of all, you need to know what it means for a function to be measurable. So a measurable function, basically, we look at functions from our domain into the real numbers, but we need, ultimately what we're going to try to do to integrate that function is take the inverse image of these intervals in the range, right? Right? So to do that, we need to make sure that the inverse image of those intervals is measurable, is a measurable set.
Mm-hmm.
Does that make sense?
Yeah.
So, what do we require for a function to be measurable? Well, that's all we require. We require that the inverse image of measurable sets are measurable. That's what it means for a function to be measurable. Okay? Now, the idea is that many measurable functions can be approximated by simple functions. And that's how you take the Lebesgue integral. And basically, if your function is positive, so here's what you do. You consider a positive function first. Okay? We can't deal with negative functions yet, but deal with a positive function first. Look at the supremum over all the simple functions which are pointwise less than equal to that function. So look at all these linear combinations of indicator functions over sets, and all of those approximations of f via simple functions, all of those approximations are always less than or equal to f, pointwise. Okay? You take the supremum over all possible integrals of those simple functions. The integral of those simple functions you can just do automatically by measure theory. Because remember, a simple function is just a linear combination of indicator functions. So its integral is just the linear combination of the measures of the sets, which are represented by the indicator functions. Okay, so that's the integral of a simple function. You take the supremum over all integrals of simple functions, which are pointwise less than or equal to your function f that you want to integrate. And that is the definition of and if that supremum exists, that's your Lebesgue integral. Okay? Assuming the function is measurable. And so what this looks like in the Riemann integral, you can just visualize as picture a nice function in one dimension, picture basically the simple functions, which, it's literally just the Riemann integral. So all the Riemann integrals can be represented by this process of, it's like the lower integral, right? Where you represent the function essentially as like a constant value, which is its infimum on every interval of your Riemann partition. And then you just send the partition to 0 in width. So I think there's the intuition behind Riemann integration can be quite helpful. And it turns out that one of the key results of this theory is that if you look at the Riemann integrable function, they're not closed. They're not complete. They're not complete, basically, with respect to that norm. I believe it's the L2 norm. It might be the L1 norm. It's either the L2 or the L1 norm. Essentially, the Riemann functions integrable functions are dense but not complete, and so you take their completion, you get the Lebesgue integrable functions. It's almost like taking the rationals and completing them to get the reals. You're basically completing the space of Riemann integrable functions with respect to some inner product, which I believe is the L1 or the L2. I actually think now that I think about it, I think it's the L1 norm. I'm not exactly sure. Yeah, okay, it's the L1 norm. It's the L1 norm. It's not the L2 norm. I was wrong. It's the L1 norm. And yeah, you complete with respect to the L1 norm to get the Lebesgue integrable functions. The L1 norm of a function is you just integrate its absolute value. Okay? And then what I was saying earlier about functions that are positive, you basically define the integral over positive functions. Then for arbitrary signed functions, you split them up into their negative and positive pieces. And then you integrate those separately, because you know how to integrate a piece that's fully negative. You just take its negative and integrate it as a positive function. Does that make sense?
Yeah.
So, yeah, that's basically what you need to know in a nutshell. And then you need to learn the monotone convergence theorem, the Lebesgue-dominated convergence theorem. There's a lot for you to learn, but you can really learn. You can learn it all in like a year of rigorous study.
Yeah. Okay, sweet. That's good motivation to study.
Oh yeah, no, I mean, and the thing is, yeah, measures are used all the time because it's basically more flexible, right? It's more flexible than, it allows you to basically put arbitrary mass distributions over your space and understand mass distributions that are far more complex than previous, because basically anything that you can represent, not even represent, but can cover, this is the thing is, the sets that you can cover by cubes, and then basically take the infimum over all those coverings of cubes, right? Those are the possible sets. So it's a huge amount of sets that are measurable. It's way more than what sets you can just do the normal integral over.
Yeah.
You know?
Wow, yeah.
There is one technical detail, which is that you actually, after that cube-like construction, you further define, you add on to the sets which you can measure, and you include not only all those sets that I just described, but any set whose Lebesgue measure is 0, so the infimum over all those cube coverings is 0, any subset of that set, you declare it to also have measure 0. So you get all possible subsets of sets which have measure 0. So you can have very wild sets that have 0 measure. Very wild sets that have 0 measure. And then you can obviously add those sets which have 0 measure. You can take their union with normal sets that have positive measure, right? Mm-hmm. So I recommend the book Measure Theory by Paul Halmos to just get started. I think that you should start looking into measure theory before you start attacking real analysis. I would recommend the book by Paul Halmos first on measure theory. Once you learn some measure theory, I would highly recommend you check out Angus E. Taylor, The Construction of Angus E. Taylor, because it's going to have some nice advanced review of foundations. But then when you can even skip that, you can skip the review if you understand it and go straight to the measure theory setup.
Yeah.
The way he does measure theory is excellent. He constructs the Lebesgue integral in a way that's rigorous, but also faster than a lot of other textbooks, and really great intuition. But you should also consult like a measure theory textbook.